Welcome back to QST Prep Academy. Today, we are diving into an absolutely crucial standard for your certification exam, EPA Method 2G. Look, if you're aiming to be a top-tier stack tester, you've got to know this one inside and out. So grab your notebook and let's get into it. Here's a quick look at today's study guide, formatted perfectly for your mobile screen. We're covering the Method 2G overview, jumping into 2D probes, taking a quick exam prep break, tackling those stack gas velocity formulas, and finishing up with a final review.
All right, Section 1. Welcome to QSTI Academy, your exam blueprint.
Moving right along to Section 2, Method 2G, Overview, Solving for yaw. So Method 2G is specifically designed to determine stack gas velocity and volumetric flow rate using two-dimensional probes. Now you might be wondering, why do we even need a whole specific method just for this? Well, it's because stack gas rarely ever flows in a perfectly straight line up the stack. Standard measurements can actually get totally skewed by vortex flow, which is exactly why we first need to define and really understand the yaw angle. Imagine you're looking straight down into a stack. Instead of the gas hitting you right in the face, the yaw component is that flow swirling to the left or the right from the center axis. Method 2G exists specifically to measure and correct for that sideways swirling action. Okay, so once we figure out that yaw angle, we can calculate what the EPA calls the near-axial velocity. This calculation is brilliant because it successfully accounts for that yaw, giving us a much more accurate picture of the gas actually moving up the duct. But, and this is absolutely crucial for your exam, you have to remember its limitation. It does not account for the pitch component of flow. Pitch is the gas moving towards or away from the test port wall, and 2G just doesn't cover that. Okay, on to Section 3, the 2D probes, equipment and rules. Knowing the theory is great and all, but knowing the actual hardware is what gets the job done out in the field. When it comes to probes, you basically have a couple of choices. You can go with a classic Type S pitot tube, as long as it has an external tubing diameter of at least 3/8 of an inch. With a Type S, you're going to have to perform manual or automated yaw nulling. Your other option? You can actually use a 3D probe, but, and here's the catch, you must operate it purely in a two-dimensional mode. That means that pitch measurement we just talked about is dropped entirely. Now, for the exam, you need to have these core calibration points locked in. Specifically, the wind tunnel calibration location has to be rigorously verified for axial flow. That means both your yaw and pitch angles must be within plus or minus 3 degrees of zero. No exceptions. You also have to document the reference scribe line rotational offset, or RSLO. Basically, this offset ensures that the physical markings on your probe perfectly match the true aerodynamic zero that you found in the wind tunnel. So what does this yaw nulling procedure actually look like in the field? It's kind of a dance. First, you insert and position your Type S probe right at the transverse point. Then you rotate it until your differential pressure gauge hits absolute zero. That's your null. Next, read the angle on your inclinometer. Finally, you carefully rotate it exactly 90 degrees back into the flow to take your velocity pressure reading. That sequence right there, that is the absolute heart of Method 2G fieldwork. All right, Section 4. QST exam prep break. Time to pause. Before we tackle the heavy math, let's take a quick breather. If you want to pass the QSTI exam and get that certification, you really need the right study materials. You definitely don't want to be guessing when it comes to EPA methodologies, right? So do us a favor and hit that subscribe button right now so you never miss a study guide. And seriously, if you want to pass the QSTEEP exam, send an email to qsteepprepacademy@gmail.com. Go ahead, write that email down, reach out to us, and let us help you secure that certification. Okay, break time is over. Section 5, Stack Gas Velocity Formulas. The math. Let's get into it. Focus in on the top half of your screen for the absolute highest priority formulas you'll need for test day. Watch this metric near-axial velocity equation draw out. Notice that 34.97 constant? You take that, multiply it by the pitot tube coefficient Cp, and see how the square root of the differential pressure, when you combine it with absolute temperature, pressure, and molecular weight, drives the whole near-axial velocity? Oh, and don't forget, you also incorporate the cosine of that yaw angle you just measured in the field to finalize your correction. Now, as this next formula writes out, you'll see the English system equivalent. The overall mathematical structure is exactly identical to the metric version, but look at the constant. It shifts to 85.49. Why the change? Because we're utilizing inches of water for pressure, degrees Rankine for temperature, and calculating our final answer in feet per second. Definitely memorize that 85.49 constant for the exam. It's going to come up for sure.
Finally, watch equation 2g minus 9 write out. This is where you scale up your traverse point average velocities. You are essentially taking your average near-axial velocity and multiplying it by the cross-sectional stack area A. Then you bring in 3600 to convert your seconds into hours and adjust everything with standard pressure-temperature ratios. That whole shebang gives you your final wet basis volumetric flow rate.
Almost done. Section 6, Method 2G, Final Review, Key Takeaways. Let's lock in one final, absolutely critical, high-yield data point before test day. Never forget this specific tolerance. The rotational position of the scribe line, or the scribe line segments, along the full length of your main probe must not vary by more than 2 degrees. Period. If you measure it and the variance is greater than 2 degrees, your physical alignment is compromised and your calibration fails outright. The EPA literally does not mess around with alignment tolerances. I'm going to leave you with a bit of a provocative thought to ponder while you study. If Method 2G strictly ignores the pitch angle, at what point of stack turbulence do you have to abandon this method entirely and upgrade to a full 3D probe analysis? Because think about it. If the gas is aggressively pitching toward or away from the wall, your 2D data is missing a massive piece of the puzzle. Think deeply about where the true limits of Method 2G lie. Thanks so much for studying with QSTI Prep Academy, and I'll see you in the next explainer.